Come back to this last talk before lunch, and we have Arindam Ghosh from IISc, and he would be talking about the flow of charge and heat in quantum critical graphene.
Okay. First, thanks to Sthitadhi and other organizers for giving me this opportunity. It's to present a recent work of ours. I'm going to be talking about experiments on something that a relatively emerging area in some form where we are looking for hydrodynamic transport in graphene, particularly when you go to very, very close to the Dirac point where the system is supposed to become quantum critical in nature. This is Aniket's, my student's PhD work primarily, and new people as well. Subroto is here. He is the mainstay as far as the theoretical support is concerned. And of course, we had a collaboration on various experimental aspects with our colleagues in NIMS. Okay, to start off, essentially, oops. Okay, very quickly, primer about different modes of charge transport in solids. Of course, you have ballistic transport where charge starts from one end of the sample and goes to the other without suffering any scattering whatsoever. And that's ballistic conduction, and in which case electrical conductance is directly proportional to the square root of density because it's proportional to the number of modes that you can squeeze in as the charge goes from one end to the other. Then we have also the diffusive transport in which charge keeps on scattering many, many times before it ends up on the other side. And in this case, there's a well-defined understanding of charge flow, which is defined in terms of the mobility of the charge carriers. You can see conductance is proportional to the mobility multiplied with the charge density. And in this cases, both this one and this one, the different time scales are the electron-electron scattering time scale, the electron-phonon inversion time scale, as well as the impurity scattering time scales are the key time scales in most of the charge transport that you see in solid state. In the diffusive time scale, the rate is determined by the electron and impurity scatterings, whereas the electron phonon as well as electron interactions are sufficiently rare in nature. The last one is the viscous one, and this is what's going to be more and more important as we get along, where the conductance is given a very different mechanism. It is in the form of a viscosity, but the viscosity is essentially given by the diffusion, which is determined by the electron-electron scattering rate, and rather than electron phonon and electron impurity scattering. One of the interesting aspects of the electron-electron scattering is it's, after all, a momentum-conserving scattering process. And this, when this happens, then the electrons, the way it moves, essentially is a meniscus which is parabolic in nature, in ideal form, and an interaction with the walls that determine the dissipation, per se. Okay, so what happens in somehow it's not. All right. Okay, so people have been looking for viscous electron flow for a while now, and one of the early experiments were the Würzburg group from Lawrence Molenkamp, where if you see the semiconductor nanowires, what happens is when you apply a large current, initially the resistance increases, and then it starts decreasing again. And this essentially was understood from the Gurzey law. Is what happens is as you push more current in, the collective kinetics of charge reduces the electrical resistance, and this is essentially our first evidence of what you call the viscous flow of charge in solids. At that time, this was mid-90s. After that, there are several other reports. For example, the palladium cobalt oxide kind of system, which is Andrew McKenzie's group in Scotland, and they found that you can see the electrical resistivity as a function of the momentum scattering length normalized by the width of the sample. Doesn't look go as the expected from the diffusive law, the blue lines. Rather, it has got a very different kind of a different behavior, again taken as an example of viscous flow. There are many new suggestions where viscous flow can be observed. For some of the Kagome compounds, where it is possible to have hydrodynamic flow with, where very strong electron scattering rates are expected. Yeah, Tell me. Yes, I'm going to show that. That's exactly what we do. We measure the LMR. LMR is the momentum relaxation length. So that's essentially suppresses hydrodynamic flow. It makes it more diffusive. So yeah, we do experimentally measure it. Okay, I think this is a good place I can change. So what happens in graphene is slightly different, and this is why it's interesting. Electron-electron interaction in graphene is extremely high because of the fine structure constant you can see is when it's renormalized by the Fermi velocity rather than the velocity of light, it goes in the order of 1 rather than 1/300 expected in a free space. That results in a Lorentz invariant quantum critical point at the Dirac point, and many of the physics starts because through ADS-CFT for mapping, many of the physics of cloud-gluon plasma and various other cold atomic gases, strange metals, etc., essentially becomes realizable in a solid-state system like graphene. Okay, this has sort of gave a lot of interesting theoretical paper in early 2000s, and I'm going to say why there was a lull in this for a while, and now why is it picking up today? So what we have is this is the standard quantum, the phase diagram. You have the whole Fermi liquid and the electron Fermi liquid, but then in between, that close to the Dirac point of graphene, you see as the temperature goes down, you see the quantum critical point, and this is the zero momentum mode where the electron and holes are moving opposite to each other, equal number, whereas in the case of in a finite momentum mode where either more charged electrons or more holes on the other side. What we expect is that if the graphene is sufficiently clean, then it's a momentum conserved scattering of electron hole plasma, which essentially is called a Dirac fluid. In this case, there is an interesting scenario that the entire physics of this can, in this quantum critical point, should be able to explain with a single DC transport coefficient, which is DC conductivity, because the electron hole scattering in this zero momentum mode is expected to take place at the Planckian scattering rate, essentially determined by the uncertainty principle. Very similar to what is suggested in the bad metals in the high TC superconductors and so on. Okay, so if I summarize this, if you want to have this electron-electron scattering as the main dominant scattering mechanism in a solid-state system, you have got a hydrodynamic flow rather than diffusive flow. And in which case, if you have got large number of electrons or holes, the electrical conductivity is given by the square of the density, the width squared, this is this direction, and divided by a number which is essentially effectively a viscosity of the system. Whereas, if I go to a region where the temperature becomes the only relevant energy scale, which is essentially close to a Dirac point, when I reduce the density so much that the Fermi level is very small compared to the temperature, then temperature becomes the most important energy scale, and in which case, the electrical conductivity takes an additional contact. Essentially, the universally quantized electrical conductivity is given by the Fourier square and multiplied by some universal constant, which is essentially the symmetry class, about order 1. And plus, there is a little bit of additional viscous flow. That is why it's going as n squared. So this is expected to be the electrical property. But if I apply linear response to this, and I want to measure the thermal conductivity of this, then you can clearly show from here with a standard algebra that electronic component of thermal conductivity goes inversely proportional to the conductivity, which means now the Wiedemann-Franz law is no longer valid. So this is a unique system which allows you an experimental verification is whether you are in the Dirac fluid regime or we are in standard diffusive or ballistic regime. So this is what we are going to use. So just a quick, so just this is the most important aspect, that we have the Dirac fluid. The electrical conductivity is entirely determined by the universal constant and the thermal conductivity here. The interesting experimentally that this number has never been observed experimentally till today, and which is why all the lots of discussions about whether graphene's electrical properties are universal has essentially been shelved for a very long time, because experimentally we could never observe the universal electrical conductivity or thermal conductivity in this form till for about 20 years now that graphene physics or the experiments on graphene has taken place. Okay, so why there's a problem? Why is it never observed? So if you take a look at the phase diagram, the problem is at very large temperature, when your temperature goes above 200 to 300 Kelvin, which is room temperature, the phonons come in because we are talking about solids, and the electron-phonon interaction essentially breaks the momentum relaxation, or it's a momentum relaxing scattering, and hence hydrodynamic flow is essentially destroyed. Whereas if you go to other end of the story, which is essentially the close to lower temperature and closer and closer and closer to the Dirac point, where you expect system to be quantum critical, the disorder in the system essentially breaks the graphene into inhomogeneous patches of charged electrons and holes. So what happens is you are left with an extremely tiny area, tiny phase space in which you can look for such physics, which is why there have been theoretical calculations on where exactly you can look for Dirac fluids, but these are essentially, a tiny phase space around 200 Kelvin and fairly close to the Dirac point where the electron-electron scattering can exceed the rate of impurity scattering and phonon scattering. But these are calculations. It has not been observed so far. So if you look at the movement of graphene as a field since 2004, originally the electrical mobility of graphene, which essentially is a marker or a benchmark of how good or how clean your system is. You can see that originally it came with a low mobility graphene. The quantum Hall effect was measured, and then by the time it increased to about 100,000 centimeters per volt second, or 10,000, 20,000, the fractional quantum Hall effect was observed. But since 2016 until today, and it's over the last 6-7 years or so, it is the hydrodynamic transport that has been under focus in graphene's fundamental component, because now we can create samples of 100,000 centimeters per volt second. The larger the mobility, the better is the closer to the Dirac point that you can get experimentally. Okay, so where is the uncertainty today is that this was the first and probably only transport-based claim for Dirac fluid in graphene, which came from Harvard, Philip Kim's group, and Casey Fong, of course. And they saw the thermal conductivity is no longer obeying the Wiedemann-Franz law. Rather, at the zero density or the Dirac point, thermal conductivity is significantly enhanced compared to what it should be from Wiedemann-Franz law, which is this blue line. However, this was the only so far evidence that seemed to agree, but there was no minimum metallic conductivity that was quantized, that was not observed. And also, there was a peak at 75, which no one understood. And as a result, there have been a significant amount of contradiction and discussions in the literature. Shankar Das Sharma came up with a paper last year saying that there's nothing called quantum criticality in graphene, simply because all these features can be expected with the Fermi-liquid theory, within the Fermi-liquid framework, with a little bit of gap in the quasi-particle excitation. So the crux of the problem here is that we do not see an universal conductivity in graphene. That's experimentally what we need to do. In 2016, this came up. Then UC Berkeley group shows that there is a 2019, there was a report of electron-electron scattering actually going as the Planckian scattering rate. 2021, this is the Spanish group saying that, okay, there is a strong, large thermal conductivity, and this is Manchester's group, very large magnetoresistance in hydrodynamic graphene. So there are significant amount of work that's going on in this direction. So the plan today will be, I'm going to give you our experimental approach about what we do and how we look for this universal electrical transport in graphene, and ask this question: is graphene really quantum critical if you make it really, really clean? We'll show that there is giant thermal conductivity, and I am going to show you what happens to the universal DC transport. So just to understand, because we are here with a lot of theorists here, to just give you how an experimentalist look at graphene's electrical transport. Typically, when you apply electrical voltage, a gate voltage in graphene, the resistance decreases because you incorporate charge, either electron or hole. But because if the quality of the graphene flake is not good, then you cannot approach the Dirac point very easily. So this is electrical conductivity as a function of density. There are two samples. One is a bad quality sample. This is a better quality sample. What happens is you create this mobility, which is electrical conductivity is proportional to the density. You get a mobility here. But if the mobility is large, then in that case you see this linear part. The poorer quality sample, this is the lower quality sample, the electrical conductivity saturates much before it actually goes to zero density. And this number is called the minimum metallic conductivity, which is sigma min. And these are what you call the inhomogeneity, the N min. This is the minimum density you can go to. Okay? And this minimum density is essentially because of the Coulomb impurity scattering, which is around the substrate. So a little bit of experimental detail, I just thought I will tell you because this is what the experimentalists suffer the most. Okay, so which is why if you want to get a better quality sample, the mobility becomes larger, you get lower density. So sorry, this is the lower quality sample, this is the better quality sample. You can clearly see the mobility is essentially, the N min is lower. Okay, I'll just skip this. So in our experiment, what we do is we have been able to get some experimental breakthrough, and we can incorporate graphene into layers of boron nitride, which can give extremely high quality graphene channels. These are electrical contacts. I pass a current from here to here and measure the voltage between this point and this point. That's all we do. Okay. This is a typical resistivity versus density. You can see extremely sharp gate voltage versus density, which essentially means the mobility is very large. To give you an understanding where we are in the current state of the art, so this is where we are. So I'm going to show you samples which are approximately a factor of 10 log better than the existing global standard. So that gives us the opportunity to look for this physics in the first place. So typically, this is the conductivity versus density. In our systems, you can see conductivity is no longer proportional to density. It starts, as you make the sample cleaner and cleaner, you no longer get the standard diffusive behavior. The second thing is that if I can measure mobility here, and the corresponding mean free path, the mean free path of electrons is so large that it hits the size of the system itself. These are just computed, so at these high values of mobility, the mean free path calculation is not very reliable. At least what we can say that this is the system size, the mean free path is approaching the system size, which means now the momentum relaxation is occurring primarily at the boundary of the sample rather than inside the channel. If you look at the conductance as a function of density, you can see the root n behavior, which essentially makes it ballistic in nature. But in addition to that, you can see the minimum value of density where the electrical conductivity is saturating. If I plot this minimum conductivity at different temperatures, it looks something like this, in which case it's extremely low. Again, typically for those who have done experiments in this, these are usually in the order of 10 to the power of 11. We have got down to about a factor of 10 or more below the standard graphene channels. In addition to that, this part, this value of impurity increases with increasing temperature, showing that at zero temperature, at zero density, you have got disorder-induced inhomogeneity, plus that is induced by the activation of electrons from the valence band into the conduction band, and that goes a square of the temperature, leading to this part, or this is what we call the thermal regime, and this is what is going to become important in our system, because we want to be dictated by only one temperature scale, and that's a temperature. Okay, so is the momentum scattering the question is that, are we limited by the electron-electron scattering only? It turns out that if I plot the electrical conductivity as a function of the electron-electron distance divided by the width, this is what you call the Knudsen parameter. You can see that as you decrease this number by changing the electron density, it's exactly at 1 or around 1, there is a change in the electrical conductance, which means that you are entirely limited by the electron-electron scattering rather than the electron impurity scattering. At higher values of LEE by W, it's ballistic in nature and you are essentially constant. In addition to that, you see the hydrodynamic flow is determined by the conductivity proportional to the width of the sample, and this is exactly what you see. So, upshot of the story, these are essentially characterization that in our system, extremely high quality graphene, we are after all being limited by the electron-electron scattering rather than the electron phonon and electron impurity scatterings per se. So we have ballistic to viscous crossover, we have quadratic dependence of the conductivity on the width of the channel, and it indicates the electron-electron scattering dominates over impurity and phonon scattering. So we can start asking questions about the next part, which is the thermal regime and the Dirac fluids. However, before we go there, if I convert the dynamic viscosity, which is this, to the kinematic viscosity by normalizing it with the mass density, what is interesting is that the kinematic viscosity is extremely high, and this is one of the key surprises when the hydrodynamics in graphene started coming in. That typically the value of kinematic viscosity is in the order of 1 meter square per second. Compare that with what water, honey, and tar. Somehow the electrons are extremely viscous in these kind of systems. Okay, now once we have the electrical conductivity done, we are in the regime of very strong electron-electron scattering, which is the main scattering source. I'm not going to try to look at the thermal conductivity, and thermal conductivity is done with Johnson noise thermometry in our systems. I'm not going to spend time here. Basically, the idea is this following. So we have this graphene sample with 2 leads, and what we do, we pass an electric field, we apply an electric field, and hence a current flows, which causes a Joule heating of the system. Now, when you have the Joule heating, the electron temperature changes, and electron temperature is directly proportional to the square of the electron temperature. If you just solve this equation, it's a square of the electric field, which means at sufficiently large electric field, they will be proportional to each other. The change in electron temperature is proportional to electric field that you apply, and it is hottest over here and the coolest at the 2 leads. So you can do the averaging. Eventually, you get a very nice closed form structure that is average electron temperature is directly proportional to the electric field, and the proportionality constant gives you the Lorentz number. So this is the technique that we use to understand the thermal conductivity or electronic thermal conductivity in graphene. That's the experiment. Okay, so this is how it looks. If I this is a particular sample. I'm going to give you an example with one particular sample here for the time being. You can see electrical resistance versus density. I measured the electron temperature as a function of E at different densities from 0.55 10 to the 12 to very close to a Dirac point. And you can see the slope varies dramatically, a massive change in slope, which means that the Lorentz number is very, very different. It changes by a very large number as you tune the electron density from the Dirac point here to the large densities somewhere here. So which means Wiedemann-Franz law is out of equation. We do not have Wiedemann-Franz law because Wiedemann-Franz law doesn't depend on the electron density. So I will show you the fit essentially fits reasonably well with this particular equation, and that allows us to get the Lorentz number. It's true for various temperature and densities. I'm going to skip this. This is what we have done mostly. But what is interesting here is that if I now plot the Lorentz number in this extremely high quality graphene as a function of density, you can see that at the Dirac point, the Lorentz number exceeds that from the Wiedemann-Franz law by 300 times. So it's 300 times more thermally conducting than what you expect for a diffusive system. If you go away from the Dirac point and go on both sides at the hole dope regime or electron dope regime, it drops by 6 orders of magnitude. There is no system that you can tune the electronic thermal conductivity by 6 orders of magnitude by simply changing the electronic density by using a gate voltage. Yeah. Yeah, so these are at low temperature. This data is taken at about 20 Kelvin. At high temperature, I'm going to come to this, there are phonon contribution that comes in. Here, there is no phonon contribution. Yeah, that's right. Okay, so it's a giant violation of the Wiedemann-Franz law. Now, one of the quick point is that you can see the 6 orders of magnitude of variation can actually be captured quite nicely using the effective Lorentz number that can be described with the hydrodynamic equation of where it essentially goes as 1/4 power of density at large values of density. Anyway, again, just a quick comparison with the Harvard group result a few years ago. The change at that point of time was of a factor of 20, but I think because as you make the system cleaner and cleaner, you get very much larger violation of the Wiedemann-Franz law in graphene. Okay. Oh, sorry. So this is the temperature dependence. Abhishek, for you, this is at lowest temperature, about 20 Kelvin, the black one. If you start increasing the temperature, at the Dirac point, there's a very rapid decrease in the Lorentz number, and then overall, away from the Dirac point, the temperature dependence is lower. The phonons really come in after about 200 to 250 Kelvin. In graphene, the electron-phonon coupling is reasonably weak, so we don't see too strong phonon coupling as such. If I plot the thermal conductivity by just multiplying the electrical conductivity with the Lorentz number, you can see that at a temperature of about 100 Kelvin or so, the thermal conductivity starts becoming non-monotonic. It increases rapidly. Close to the Dirac point. Away from the Dirac point, essentially is thermal conductivity is always significantly lower than what you would expect from the Wiedemann-Franz law. The dashed lines are expected Wiedemann-Franz law behavior. Why this weird temperature scale? It turns out that this temperature scale is why the inhomogeneity, where the inhomogeneity of the solid state systems are different from very clean systems. What happens is, if I take the inhomogeneity or n impurity to approximately be 10 to the power 5, 10 to the 10 centimeter square per centimeter square, and I convert that into some form of a fluctuation in the local Fermi temperature, then it turns out that fluctuation or root mean square is in the order of 80 to 100, which means that as I go closer with my Fermi energy goes closer and closer to the Dirac point, below 200 Kelvin, I actually am seeing a frozen charge distribution. So I'm no longer being able to probe the thermal behavior. The thermal behavior becomes apparent only when the temperature is above this kind of a temperature and sufficiently low from phonon temperature. So this is why this was not being observed for the last 20 years, because we simply didn't have good enough samples so that the T impurity would be sufficiently low. Most of the cases, T impurity had been nearly room temperature, and this is where we have been able to come down to a certain extent. Okay, in this region, the thermal, if I plot, I have got the thermal conductivity as a function of temperature and density. I have got electrical conductivity as a function of temperature and density. So at the same temperature and density, I plot the value of at the Dirac point, and for different temperatures, I plot thermal conductivity as a function of corresponding electrical conductivity. And as you can see, no longer electrical conductivity and thermal conductivity are proportional to each other like what Wiedemann-Franz law expects. Instead, they are actually inversely proportional to each other, what the Dirac fluid expects to give us. Now, what do we have here? We have a system in which now we can look for the universal electrical conductivity by rearranging this equation. Thermal conductivity is inversely proportional to electrical conductivity, and each and every of these terms are now experimentally accessible. For example, this is here. We had just calculated by Johnson noise and electrical transport. The thermal conductivity, the enthalpy density comes from the fitting of the Lorentz number with density, and the LMR, the momentum relaxation length, is essentially either the width of the sample itself or the mean free path, depending upon which one is shorter. So each and every component of this is essentially experimentally determinable. So what we did, we just calculated it. And now when we do it, you can start seeing that near the Dirac point, or the charge neutrality point, below 100 Kelvin, things are inhomogeneous. I do not put too much importance here. But as you go higher and higher temperature, these numbers starts converging into something which is relatively well defined. And this is roughly 4 E² by h, or comes to close to that. So what we do after that is we calculated this as a function of temperature normalized with a Fermi temperature. And this is 6 different samples of different disorder, but all at very clean systems. You can see that when you calculate the sigma q, the universal DC conductivity, as you go closer and closer to the thermal regime, where the Fermi temperature over the actual temperature, electron temperature, is smaller than 1. So this is the degenerate thermal regime. We end up getting first experimental verification of the universal DC conductivity in graphene, which is quantum critical in nature. Okay, this is very good. I think what we do is that we ask the question, okay, so what happens if I compare that with actual experiments? So you can see the electrical conductivity for different disorder samples. When I calculated by extrapolating electrical conductivity to 0 density, that is this one, sigma min, you can see there is no quantization, there is no interesting behavior, and they are very, system dependent and disorder dependent. Whereas if I calculate the value of electrical conductivity by combining the thermal and the electrical conductivity, we essentially start getting a far more well-defined universally quantized number. So we are very confident that we have the first evidence of quantum critical behavior in graphene at extremely high quality. But that's not all. So I'm going to finish in the next 5-6 minutes by giving you the next step, was what we want to do. Essentially, we ask the question, okay, if you have a quantum critical system now, and we ask and we have a flow, we have a hydrodynamic flow of charge, then can we look at the possibility of minimally dissipative flow of electrons in our system, which essentially, various theories, and if you have temperature as the only energy scale, then the shear viscosity over the minimum shear viscosity normalized by the corresponding entropy is supposed to be larger than the universal quantum number of h cross over 4 pi kb, this old experimental holographic limit for minimally dissipative flow. Can we get there? Can we understand whether this is true in our system as well? Now, it turns out that we can calculate and we can estimate experimentally what the value of eta, the thermal viscosity, shear viscosity should be. These are done by Subroto. Subroto helped us in deriving all these, so if you don't agree, you have to talk to him. So typically this is given by the thermal entropy density multiplied by the scattering time. The scattering time is, after all, a Planckian scattering, so we can take that as h cross over alpha squared kBt, where alpha is electron-electron scattering. And this number then, h, because electrical conductivity is directly proportional to, inversely proportional to h here, I get this value of h by simply taking a derivative of sigma with respect to n squared. As you can see in our sample, sigma goes as quadratically with density at low values of density. This is where a transition from ballistic into the thermal regime occurs. So what we do here is that we take experimentally the value of this derivative and we plug it in here and get a value of the estimation of the viscosity. This is how it looks. The viscosity as a function of temperature goes a square of temperature at sufficiently large. In this region, below 100 Kelvin, it is inhomogeneous. So this is the part that we trust. And now what we do is that we know thermal entropy density, and we know viscosity. We take the ratio, and we take the ratio for various different samples. And this is very exciting, because what we see is that as you go to larger and larger temperature, which essentially is thermal regime temperature becomes larger than the all other energy scales, you start approaching the universal h by 4 pi in the cleanest of samples. So this one is lowest n min, or the disorder. This one is the highest disorder system. So as you make the system lower and lower in disorder, you start approaching the value of the minimal holographic limit in graphene of perfect fluid. So that's what I have. This is the conclusion. We have been able to get a new regime of mobility and cleanliness in graphene that allows us to ask new questions of graphene and its application, or whether a condensed matter system can be a nice playground to look for high energy theories and various cosmology and various other high TC superconductors, whether we can get into that area now. We have very large thermal conductivity and complete destruction or breakdown of Wiedemann-Franz law. We have the first derivation of the universal conductivity of graphene, and we have now verified what theoretically was expected many years ago of electrical conduct. This scale is 4e squared by h, and possibly we approach a minimally viscous electron fluid in ultra-clean graphene channels. I'm hoping this paper will come on archive very soon. Thank you very much for your attention.
Thank you, Arindam, for the nice talk. Questions? Okay, let's just go to Abhishek and then.
Abhishek.
This large thermal conductivity, I guess you observe it in the hydrodynamic regime, right? Is that right?
Yeah, that's right.
Okay, no, it's because I mean, at least in 2D hydrodynamics, there's a prediction that the thermal conductivity should in fact diverge with.
Exactly, and it does so. We have got.
You have.
Yeah, at low temperature. It has to be
at low temperature.
It has to be at low temperature.
Yeah.
Yes. At
So
low temperature.
it diverges as you increase the the dimensions. Like there's a logarithmic.
No, we have not done as very systematically as a function of dimension. Most of our samples have got about a couple of microns by couple of microns, or maybe a little bit more. We are seeing as you decrease temperature, the thermal conductivity diverges as you go to lower and lower temperature. But yeah, it diverges about hundreds of times above the Wiedemann-Franz law.
Okay, but I guess maybe you can see the size.
Now, good.
That's probably...
Thank you. It's an experimental idea. We need to talk about it.
Rasif.
Hi, very nice talk. So you said that, below about 100 Kelvin, you are going to get dominated by disorder. You see the inhomogeneities.
That's right.
But your violation of Wiedemann-Franz law was largest at around 20 Kelvin, if I look at that graph. Is that something that we understand? Because at that point, you should not be hydrodynamic as such.
Okay, no. Wait, I think... Sorry, it is true that at the Dirac point, the violation of the Wiedemann-Franz is largest at low temperature, but that doesn't mean that it is not hydrodynamic. We are essentially with a flow of, the electron distribution is inhomogeneous, but it's still within the patches of electron and hole, it is hydrodynamic in nature. It is not something that is determined by the diffusive transport, even at that temperature. But at the same time, if you go to higher densities, at all temperatures, the thermal conductivity is way below that you expect from the Wiedemann-Franz law. Which essentially means that the Wiedemann-Franz law diffusive behavior is simply not applicable to these systems in any form.
Abhishek.
So maybe you already explained this, but I missed it. How do you measure the thermal entropy? For the last part?
The entropy. Yeah. Good point. Yeah. So what we do is essentially we look at. I'm sorry. There's a delay between me pressing it and that happening there. So I'll show you this. We actually measure entropy experimentally, right? So what happens is when you go to the Lorentz number, the Lorentz number is directly proportional, or directly proportional to the. There you go. So when we measure Lorentz number as a function of density, we fit it with a hydrodynamic flow that goes as 1/n to the power of 4. At zero density, the Lorentz number is directly and multiplied by the scale in density gives me an experimental estimation of the thermal entropy. Then you take the Gibbs relation with the thermal relation. Thermal entropy is proportional to T multiplied by the entropy, and you get directly the entropy. Actually, experimental validation. I can show you this calculation.
Sorry, I had a follow-up.
Yeah.
The lower bound for the entropy to the viscosity to entropy ratio. What kind of systems do you expect it to actually saturate the bound? Like I know the Schmalian et al. Papers said that you can do it in Dirac systems, but is it any quantum critical system, or is it something special to Dirac?
Well, I mean, there are violations of that as well, as far as I understand. What we have been trying to do is we are simply trying to see if what kind of number we get, because we are doing this experiment. We are not trying to fit it to a particular model here, but we can measure the value of both eta and S experimentally. We just took them and divided it, and we found that at the lowest of temperature, in the cleanest of devices, it seems to I mean, if you calculate the value of eta over S, it approaches within a factor of 4 the bound. Now, whether it's other quantum critical systems will show the same thing or not, that will probably go into the details that I don't know.
Shobhan.
Yeah.
You showed some inverse power dependence.
Correct. Right.
Do we understand why that is so, or is it?
Yeah, we can understand. That's actually fairly straightforward. The Boltzmann equation, essentially. Okay. And in linear response, you can derive it straightforward.
Yeah, I have a very naive question.
Sure.
So for a quantum system, this entropy means experimentally how generally we measure, because entropy, how I see is it's a state function. I have to know the state and
so that is why we have to calculate from the Lorentz number. It's a ratio of two transport properties. You see, thermal conductivity divided with electrical conductivity. That is what gives you an estimation of the state function. You're absolutely right. I mean, you cannot get the state function from a transport measurement. But if you take a ratio of the two, that comes out to it ends up giving you the thermal entropy.
More questions? Okay.
So will there be an advantage if you go even lower in temperature, because there'll be like less contribution of phonon fluctuations? So will there be an advantage?
Yeah, there is always an advantage to go to lower and lower temperature, because you can see many of these physics are zero temperature physics. But the problem is that going to very low temperature, then I get determined by the inhomogeneity. And then experimentally, I am not in a very good space. So as we make the sample cleaner and cleaner, we will be able to go lower and lower. The reason we could see this is simply because we have been able to come down to sufficiently low temperature where my phonons don't kick in and destroy my results. So I have been able to get about 200 Kelvin of temperature window where phonons are not that much very strong. Inhomogeneity is not too strong. So I'm able to get the quantum critical conductivity in that region. But, so if I clean the system up, I will be able to go to low temperatures.
Oh, okay.
So Arindam, just out of curiosity, at this level of cleanliness, lack of disorder, etc., does puddle formation come out, and if so, at what temperature?
Low temperature. So that's what, if I take this as the typical inhomogeneity, and I convert this into an effective fluctuation in the Fermi temperature, so that's the temperature scale below which it's inhomogeneity. It's about 80 to 100 Kelvin. Yeah. So in spite of doing all sorts of song and dance and cleaning the system, I'm still just at 100 Kelvin. If I could clean it even more by another 100 times, I will go to 10 Kelvin. I think there's a whole new regime of physics that will come up.
I'll just ask a quick question. In your plot of effective Lorentz number, you showed that, I mean, for even the largest deviations from the Dirac point, it never obeys Wiedemann-Franz.
No, it doesn't.
Okay. So is that does this mean that in this entire region, it's a Dirac fluid?
Yeah, so that's so this is what we don't understand.
Yeah.
Absolutely. So, I mean, typically this deviation, I'm happy with it if it happens only here. But it seems that this thing is actually going to very large densities. In this region, probably it is deviating a little bit here, but the fact that it agrees too well over too long a density range, and I'm a little uncomfortable about it. Here it should be Fermi-liquid, right? And it should behave. Maybe Subroto will be able to say better than me here. But if you fit it, it fits so beautifully, and so I don't mind so showing it. But yeah, you're right. I mean, we do not know why it fits so well the Dirac fluid behavior over the entire density range.
Is there an experimental way to draw the crossover curves that you were showing for your samples?
Crossover of?
From the Dirac liquid to more like...
Yes, yes. Well, I mean, we are still trying to find, our initial attempt was to show electrical conductivity as a function of the electron-electron distance. And we saw that we started seeing a deviation at the value of Knudsen number of 1, which essentially only tells you that it goes from a ballistic to a hydrodynamic regime, but it doesn't show whether it's a Fermi-liquid to Dirac fluid. So I don't think we can say that at this point of time. No, no. There, this is the, you can see as a function of Knudsen number, this is the ballistic regime, this is where it starts becoming viscous and the conductivity drops.
Can I just make one comment regarding that?
Sure.
Yeah. When you are sufficiently away from that regime, you know, around n equal to 10 to the power 3, am I correct in assuming that you still have a strongly interacting?
Yes. Yeah, so we always have very strong
we basically expect Wiedemann-Franz to be holding in that regime. I mean, otherwise, you know, why it is going down could be...
That's right, I don't know. That's exactly what I was answering to, you know, Subhro. I really don't know why it fits so well all the way up to high density.
The point was that it's never a weakly interacting Fermi gas.
Well, it should be at such a high density. At largest density, it should be weakly interacting, but we see strong interaction.
Yeah,
so we don't know.
We should discuss. Very quickly.
Right.
Question.
Sure.
In those curves, the Wiedemann-Franz law violating curves, if hypothetically I extended the density to go to the Fermi-liquid phase, how do the curves change?
Right. So that's what. That's exactly. It should become flat. And no, actually, what we would expect if it's a Fermi-liquid, then Wiedemann-Franz law, the effective Lorentz number should become Wiedemann-Franz law. I'm still sitting at a number, even at the highest densities, which is 3 orders of magnitude lower than what is expected from Wiedemann-Franz law. You see, this is normalized with Wiedemann-Franz law magnitude. So at some point of time, it has to come up. I don't know when. Yeah, eventually. And theoretically, when people calculated, they showed that it does go up, but we have not reached that.
Okay, so let's thank Arindam once more for the nice talk.
Thank you.
And the discussions. At this point, we break for lunch. The lunch should be outside, and we regather here at 2 for the next session.